Hello, my name is Stefan, and my research proposal was on assessing the viability of nitinol woven liner for use in prosthetics for lower limb amputees. First, I will be diving into the state of the art of prosthetic liners, specifically the current materials used in liners and problems seen with these specific materials by prostheses users. A prosthetic liner is used to improve comfortability in prosthetics in lower limb amputees by providing a cushion between the hard socket of the prosthetic and the amputee's leg. Two of the main materials currently used are elastomers and silicone. One of the main drawbacks of both of these materials is them having a very low thermal conductivity, which does not allow for heat to escape from the liner, causing a variety of issues. In a study completed to determine the issues of importance for lower limb prostheses users, researchers found that one of the most important issues to users was the ability to avoid getting rashes while using a prosthetic. In the same study, the ability to prevent the prosthetic from smelling badly was seen to be an issue of moderate importance to these same users. When it comes to silicone liners, more than 40% of amputees surveyed in a study completed by a group of researchers reported itching, perspiration, eruption, and odor. Beyond the previously mentioned skin problems, the use of a liner can also cause a variety of infections and hyperhidrosis, which are directly caused by the low thermal conductivity or aeration of liners. In essence, allowing from heat to move through a liner properly is very important for the comfort and health of amputees, and finding a solution for this issue will greatly improve their quality of life. Next, I will be diving into the state of the art of nitinol, specifically what is nitinol and how it can be used to solve problems in the state of the art that were previously mentioned in the state of the art for prosthetic liners. Nitinol is an alloy made up from nickel and titanium. Due to nitinol's biocompatibility, it is used in many biomedical devices such as implantable devices, surgical instruments, and dental devices. Some of the important qualities which nitinol possesses are its shape memory effect, its superelasticity, and its high thermal conductivity. The specific quality which nitinol possesses, which makes it important for this research, is that of a very high thermal conductivity, 10 watts per meter Kelvin, which is much higher than the common elastomers and silicone, which are used in current liners, which have thermal conductivities ranging from 0.09 to 2.5 watts per meter Kelvin. The high thermal conductivity of nitinol makes it a prime candidate to be used within a liner of a lower limb prosthesis. However, nitinol alone cannot be used for liners due to it being a metal which does not possess the same compressive properties as the polymers currently used and would in turn create a very uncomfortable environment for the user. This is where the idea of a nitinol threaded elastomer liner comes in. By weaving together layers of nitinol threads within the yarn of an elastomer, the product would have the mechanical properties of an elastomer, which are primed to be used within a liner while having a higher thermal conductivity, allowing for better heat flow, enabling many of the issues prostheses users meet to be solved. Threading nitinol with a polymer is something that has not been done previously regarding medical devices, and success in this study would enable a whole new branch of nitinol woven polymers into the medical device sphere. Next, I will be diving into the specific aims of the study, specifically using the ideas discussed in the previous sections, how we can prove that integrating nitinol into liners would create an improved liner. The first specific aim is testing the mechanical properties of liners by varying thread diameter and mixing ratios of nitinol and elastomer to evaluate their similarity to current liners. The planned method for creating these liners is to use a very small diameter nitinol threads and weave them together with threads of elastomer to create essentially one material. Using a range of sizes of both nitinol and elastomer threads, as well as a range of mass fractions of both materials, samples will be created with ranges of each of these different parameters. The samples will be patches of consistent size, about 5 millimeters thick and 10 millimeters with length and width, and will then be exposed to a compression test normal to the direction of the threads. A control sample will be taken from elastomer currently used in prosthetic liners and be used to compare which combinations of thread diameter and mass fraction best match previously existing liners. This procedure will then be repeated after soaking the samples in water to determine the effect of moisture on the samples to simulate sweating. Both tests will be repeated 1 million times for fatigue analysis to determine what impact fatigue will produce on the compressive modulus. If the elastomer nitinol weave material created for this testing does not adequately perform on the tests in comparison to pre-existing elastomer liner, different methods of weaving elastomers and nitinol together will be studied to solve this issue. The second specific aim is testing liner samples to evaluate the thermal conductivity of nitinol elastomer liners in comparison to current liners. More samples following the dimensions specified in AIM 1 will be created using the materials selected in AIM 1, which had properties that match the currently existing liners. Samples will also be created and tested using the pre-existing elastomer liner as a control group. These samples will then be exposed to a steady state heat conduction heating test where a constant temperature field is fed through the sample for an extended period of time, allowing for a calculation of the material's thermal conductivity. Similar to AIM-1, this test will be repeated with silk samples, and testing both wet and dry samples will be repeated 1 million times to view the impact of fatigue. In this test, materials which have a much higher thermal conductivity than the control group will be those which will move forward to further testing. Finally, for specific aim number 3, testing fully built out liners in an in vivo setting to prove viability in use. In this phase, fully built out liners will be built using materials which were shown to see an improved thermal conductivity in AIM-2, and testing will be conducted to evaluate a variety of properties, including compressive elasticity, shear elasticity, tensile elasticity, and coefficient of friction. Testing for compressive shear and tensile elasticity will be conducted using a material tester as well as custom fixturing. The data collected from the material tester will then be used to calculate the elasticities of different materials. When it comes to the friction testing, a planar friction tester will be used to evaluate the coefficient of friction between the elastomer and the human skin. In conclusion, there are many issues with the current liners used in lower limb prostheses, and many of these issues relate to the lack of thermal conductivity that elastomers and silicone, two of the most common liner materials, present. Nitinol, being a great thermal conductor, would seem to solve these issues. However, due to its properties as a metal, it would be unable to provide the comfort that current liners provide. To solve this, it was decided to weave together two materials to create an elastomer liner. The 3 specific aims of the study hope to enable the final elastomer nitinol liner to solve the internal climate issues seen by current liners while not compromising the comfort of these same liners. Testing for the mechanical characteristics of the material allow for it to best act like an elastomer liner, as elastomers are heavily used in liners specifically for these properties. Next, testing for the thermal conductivity of the material allows for confirmation that there is an improvement in comparison to elastomer liners, as this is the largest downfall of current liners. Finally, running in vivo tests allow for final confirmation that the materials will work when in use by lower limb amputees. Overall, this research aims to provide an alternative material to be used in future liners, which will ideally prevent users from experiencing the many current downsides to liners relating to their internal biome. Thank you for listening to my research proposal, and leave any questions below. Thank you.